In mathematics, the idea of a free object is one of the basic concepts of abstract algebra. It is a part of universal algebra, in the sense that it relates to all types of algebraic structure. It also has a formulation in terms of category theory, although this is in yet more abstract terms. Examples include free groups, tensor algebras, or free lattices. Informally, a free object over a set A can be thought of as being a generic algebraic structure over A. The only equations that hold between elements of the free object are those that follow from the defining axioms of the algebraic structure. Definition: free objects are the direct generalization to categories of the notion of basis in a vector space. A linear function u, e1, e2 between vector spaces is entirely determined by its values on a basis of the vector space e1. Conversely, a function u, e1, e2 defined on a basis of e1 can be uniquely extended to a linear function. The following definition translates this to any category. Let be a concrete category, let X be a set, a C an object, and I, X F a map between sets. We say that A is the free object on X if and only if they satisfy this universal property. For any object B and any map between sets F, X, F, there exists a unique morphism G, a B such that F equals FOI. That is, the following diagram commutes. In this way, the free functor that builds the free object A from the set X becomes left adjoint to the forgetful functor. Examples: the creation of free objects proceeds in two steps. For algebras that conform to the associative law, the first step is to consider the collection of all possible words formed from an alphabet. Then one imposes a set of equivalence relations upon the words, where the relations are the defining relations of the algebraic object at hand. The free object then consists of the set of equivalence classes. Consider, for example, the construction of the free group in two generators. One starts with an alphabet consisting of the 5 letters. In the first step, there is not yet any assigned meaning to the letters, or these will be given later, in the second step. Thus, one could equally well start with the alphabet in 5 letters, that is, in this example, the set of all words or strings will include strings such as E, B, C, D, A, B, D, C, and so on, of arbitrary finite length, with the letters arranged in every possible order. In the next step, one imposes a set of equivalence relations. The equivalence relations for a group are that of multiplication by the identity, and the multiplication of inverses. Applying these relations to the strings above, one obtains where it was understood that C is a stand-in for, and D is a stand-in for, while E is the identity element. Similarly, one has denoting the equivalence relation or congruence by, the free object is then the collection of equivalence classes of words. Thus, in this example, the free group in two generators is the quotient. This is often written as where is the set of all words, and is the equivalence class of the identity, after the relations defining a group are imposed. A simpler example are the free monoids. The free monoid on a set X is the monoid of all finite strings using X's alphabet, with operation concatenation of strings. The identity is the empty string. In essence, the free monoid is simply the set of all words, with no equivalence relations imposed. This example is developed further in the article on the clean star general case. In the general case, the algebraic relations need not be associative, in which case the starting point is not the set of all words, but rather strings punctuated with parentheses, which are used to indicate the non-associative groupings of letters. Such a string may equivalently be represented by a binary tree or a free magma. The leaves of the tree are the letters from the alphabet. The algebraic relations may then be generalities or finitary relations on the leaves of the tree. Rather than starting with the collection of all possible parenthesized strings, it can be more convenient to start with the Herbrand universe. Properly describing or enumerating the contents of a free object can be easy or difficult, depending on the particular algebraic object in question. For example, the free group in two generators is easily described. By contrast, little or nothing is known about the structure of free-hating algebras in more than one generator. The problem of determining if two different strings belong to the same equivalence class is known as the word problem. As the examples suggest, free objects look like constructions from syntax. One may reverse that to some extent by saying that major uses of syntax can be explained and characterized as free objects in a way that makes apparently heavy punctuation explicable. Free universal algebras. Let be any set. Let be an algebraic structure of type generated by. Let the underlying set of this algebraic structure, sometimes called universe, be, and let be a function. We say that is a free algebra on the set of free generators if, for every algebra of type and function, where is a universe if there exists a unique homomorphism such that free functor. The most general setting for a free object is in category theory, where one defines a functor, the free functor, that is the left adjoint to the forgetful functor. Consider the category C of algebraic structures. These can be thought of as sets plus operations, obeying some laws. This category has a functor, the forgetful functor, which maps objects and functions in C to set, the category of sets. The forgetful functor is very simple. It just ignores all of the operations. The free functor F, when it exists, is the left adjoint to U. That is, takes sets X in set to their corresponding free objects F in the category C. The set X can be thought of as the set of generators of the free object F. For the free functor to be a left adjoint, one must also have a set morphism. More explicitly, F is up to isomorphisms in C, characterized by the following universal property. Whenever A is an algebra in C, and G, XU is a function, then there is a unique C morphism H, FA such that UO8 equals G. Concretely, this sends a set into the free object on that set. It's the inclusion of a basis. Abusing notation is an algebra. Correctly, it is. The natural transformation is called the unit. Together with the cownite, one may construct a T-algebra, and so a monad. This leads to the next topic. Free functors exist when C is a monad over set existence. There are general existence theorems that apply. The most basic of them guarantees that whenever C is a variety, then for every set X there is a free object F in C. Here, a variety is a synonym for a finitary algebraic category, thus implying that the set of relations are finitary and algebraic because it is monadic over set. General case. Other types of forgetfulness also give rise to objects quite like free objects, in that they are left adjoint to a forgetful functor, not necessarily to sets. For example, the tensor algebra construction on a vector space is left adjoint to the functor on associative algebras that ignores the algebra structure. It is therefore often also called the free algebra. Likewise, the symmetric algebra and exterior algebra are free symmetric and antisymmetric algebras on a vector space. List of free objects. Specific kinds of free objects include free algebra, free associative algebra, free commutative algebra, free category, free strict monoidal category, free group, free abelian group, free partially commutative group, free clean algebra, free lattice, free Boolean algebra, free distributive lattice, free hating algebra, free Lie algebra, free magma, free module, free monoid, free commutative monoid, free partially commutative monoid, free ring, free semigroup, free semiring, free commutative semiring, free theory, term algebra, discrete space.